So in this video, we're going to talk about how to solve rational equations. Up to this point in my previous videos on rational functions, we've been talking about simplifying, especially in my last video where we talked about mixed operations. We really talked about how to do with grouping symbols, exponents, multiplication, division, addition, subtraction in order to get the right answer. And it can get complicated and all comes back to order of operations. And of course, solving is going to be reversing the order of operations. Nothing is changing there. You're still going to be dealing with addition, subtraction at the bottom, and then multiplication, division. There are not going to be any exponents in Algebra 2 with rational expressions, but there is going to occasionally be a grouping symbol that has to be dealt with at the end. But rational equations are very specific, and they have specific vocabulary, as we've learned, that we need to address when solving. So let's take a look at some of those specific rational ideas about solving. So when we look at solving for rational equations, we're going to be taking a look at steps in addition to reverse order of operations or reverse Gelndas. And the first of those is when solving, you find the LCD, the least common denominator. You find it the exact same way that we've already talked about when we add and subtract. Once you find the LCD, you multiply each term by what is missing from the LCD, and this will make each denominator the same. You do that on the top and the bottom. So then once you have multiplied the numerator and the denominator by what's missing from the LCD, you'll simplify and or combine the numerators and rewrite each side of the equation so that you only have one denominator. These three steps right here are identical to addition and subtraction. So if they sounded familiar, yeah, I was just basically reviewing what we just did for addition and subtraction. They are exactly the same. You got to worry about distributing negative signs. You got to combine like terms, you have to be careful. The new step occurs right here. When you're solving, if the denominators are equal, then you can actually eliminate them because of the multiplicative property of equality. So this is not going to happen in addition and subtraction. It's going to happen only with solving because we have an equality property that says if we multiply the same thing on both sides, then it is still equal and they can possibly be eliminated. So once you have done this new step 4, you're going to solve the remaining equation. They're mostly linear and sometimes quadratic, and then you will reverse the order of operations again to solve those two equations, and that's what the grouping symbol means. So when we talk about the grouping symbol with reverse order of operations, if we're reversing the order of operations and going this direction, remember in this world of rationals, you don't have to worry about these, at least in Algebra 2. So once we get through this, when we get to this grouping symbol, we have to make sure that we solve a linear equation by using reverse order of operations or solve a quadratic equation by using reverse order of operations. And of course, quadratics have an exponent, and we'll have to deal with that by factoring. So all the quadratic elements that we learned in the quadratic chapter, they all come back again to solve these when they are applicable to this problem. All right, so now we're going to take a look at some actual examples of solving rational equations. So when you solve a rational equation, it is sometimes tempting to use cross multiplication. And the problem with that is how are you going to cross multiply this problem? It doesn't make any sense. So though it works with some problems, I don't use it because I like to be consistent. What I like to use is I like to use the LCD. Right? The least common denominator is used to eliminate the denominator from the problem and therefore make it so all you have to do is solve the remaining numerators. So the LCD of this problem would be the common number that these two numbers divide into, which would be 8. And also the variable, it also would have to be common. So this right here, again, the way a least common denominator works is you multiply what you currently have by what is missing from the LCD. So in this problem, you're missing the x from the LCD. So you would multiply it on the top and the bottom. And from this problem, you're missing the 4, right? Because 2 times 4 is 8. And now if you just kind of do a little mental check here, this is 8x and this is 8x. So both of those are now equivalent. So what you do now is you will simplify this, right? So you're going to distribute this one and multiply that one. So you'll get 4x plus 12. All right. And then that equals 5x. And that would actually be the same thing as cross multiplying. But again, when you look at this problem, cross multiplication is not going to help you. Technically, though, let's talk about algebraic, algebraic rules here. Technically, there still is an 8x here, and there still is an 8x here. And you can cancel it out. And the reason you cancel it out is imagine you had a problem like this from a previous chapter. Okay? If I had this in a previous chapter, the fact that I have the 8x on both sides means that it will cross out due to the subtraction property of equality, right? I mean, you can show the work if you want to show that it cancels out. But if you don't have to, I mean, if you have the same thing on both sides, it has the same sign and term, they cancel out using the subtraction property of equality. Well, over here, we have the multiplicative property of equality, because if I multiply both sides by 8x, it would cancel out on both sides. So you don't have to show that step. You can just get to here and say, okay, I have the same thing being divided, the same term being divided on both sides, so it cancels. But that's the reason. Is because you're using the multiplicative property of equality. So now we do just have the numerators, and now we just have an algebra 1 problem, right? This problem right here is just an algebra 1 or geometry problem to solve. I'm just going to move my variables to one side. Just going to move them to one side and then divide. So very simple, very reasonable problem, right? Once we know how to do it, it is the same thing, only different. And in fact, that problem is now done. Your answer is 12. There is one important thing to remember. We can't forget about domain restrictions. They do play an important role in solving as well. And the domain restriction here, you don't need to set 8 equal to 0. But if you set 2x not equal to 0, you would get that x is never allowed to equal 0. Why is that important? Because if your answer is x equals 0 and your domain restriction is that x can never be 0, there would be no solution. But in this problem, we're good to go. The way you would check this, by the way, is you would put the 12 back into the original problem. So if I put the 12 back into the original problem and had 12 plus 3 divided by 2 times 12, and I simplified that, that would come out to 15 over 24. And if I reduce this fraction, it should come out to 5/8. And remember how we've been talking about reducing fractions as we find a common multiplication fact. This is 3 times 5. And this is 3 times 8. And once you cancel out the common multiplication fact, that's how you reduce a fraction. I know that you didn't learn that in elementary school, but it is the most efficient and the most mathematically correct way to reduce a fraction. Okay, so let's take a look at how we would do this problem again that would not allow me to use cross multiplication. So cross multiplication, again, is something you learn in geometry, occasionally in algebra 1. It is very ineffective because of its lack of use. You can only use it under certain circumstances. However, if you use the LCD, you will not have that problem. The LCD will work every time. So what is my LCD? Please remember that this problem has a 1 on the bottom. Okay, so it doesn't need to be part of the LCD, but it will need to have, be multiplied by a couple items. So this LCD would be 6. The smallest number that 6 and 2 divide into is 6, and x. So then I would come back and I would say, well, what is this missing to become 6x? It's missing 3x. What is this missing? It has to be the same. Remember, we don't really care about the numerator. Its multiplication is decided by the denominator. All right, so down here, this needs nothing. It is, in fact, the LCD, so it does not need to be changed, but this needs the entire LCD of 6x. This next step is really important to understand how it works so that you don't make a careless mistake. So we multiply the top here, we get 9x squared. The bottom is 6x. Then this doesn't change, so minus 5 over 6x. And then equals negative 12x over 6x. It is very important to combine these like terms before you cancel the denominators. So in this case, all I have to do is combine them and put them over 1/6x. Okay, and then over here, I would have negative 12x over 6x. Though it may be tempting to reduce that, remember it would just reduce back to the original problem and would not help you. You reduce it by eliminating the denominators again, because we could multiply both sides by 6x to cancel it, but if you understand how properties work, you don't have to show that. You could just simply say that was done by the multiplicative equality property. So now you're left with this. Now you're left with 9x squared minus 5 is equal to negative 12x. And now we have a problem straight out of the most recent test we took on quadratics, right? It's the same idea. So what do we do with quadratics? We set them equal to 0. So I would add 12x to both sides. Set it equal to 0. And this problem will factor. You know, would you have to potentially do something other than factor? The answer is maybe, but you know, the focus in this chapter is, can you solve a rational equation? So most teachers won't give you the most difficult quadratic equation on top of a rational problem. So I factor this using the box method normally. If you use grouping or what have you, you may. This is a great problem to do with the box method. I'm going to try for 9x squared, which is locked in. Remember, we lock in 9x squared. We lock in negative 5. I'm going to try 3x and x. Again, if it doesn't work, that's okay, right? That's what we have to learn about any method for factoring. There is a little trial and error. So 5 can only be created by 1 times 5. So we don't have a lot of options here. So I'm going to put a 1 here and a 5 here, and let's see what we have and see if we can get this middle term, which is the goal, right? Our goal in any factoring problem is to get our middle term. All right, so when I multiply this through here, this gives me 3x. This gives me 15x. And remember, this problem is about subtracting, right? We're trying to subtract these terms to get the middle term, which is pretty easy because 15 and 3 make 12 if this is negative. Okay, so it lines up, right? And then we get our two factors. Our factors are 3x minus 1 on the top, and then 3x plus 5 along the column. And then we set both these equal to 0 using the zero product property, which we learned very recently in quadratics and came up in the polynomial chapter. So we set both these equal to 0, and then we solve. So this would be 3x is equal to 1. So x is equal to 1/3. Over here, we would have 3x is equal to negative 5, and then we would get x is equal to negative 5/3. So the question is, do these work? And there isn't really extraneous answers other than domain restrictions. So if I come up here and look, the domain restriction of this problem, again, I would set only the portion that has an x in it not equal to 0, and I would solve for, as I said, the anti-solution by dividing by 6 on both sides, right? And so I just can't have an answer that's 0. So when I come down here, the answer is good. We don't have an issue. So we can go back to using our curly brackets. The smaller answer is 5/3. The larger answer is 1/3. And again, what do these answers mean? If I plug them into the original problem, which would be kind of complicated, I would get -2. You would clearly want to use some kind of calculator to do that. But you can already see, like, if you put a third in there, it's not so bad. If you put a third in there, you would have 3 times a third, which is a half, minus 5 times 6 times a third, which would be 2. And so you would get, yeah, it would come out to the right thing. Again, if you use a calculator to see that, then it would be a little clearer. But remember, there are no extraneous answers in this section other than answers that are the same as a domain restriction. So if one of these answers was 0, I would have to eliminate it and consider it extraneous. So in these examples, we're going to take a look at problems that have a little bit more complicated LCD and therefore has more algebra to simplify before we can solve. So what would the LCD be in an example like this? Well, the LCD, as we know, is the smallest number that all of the denominators can evenly divide into, which gets complicated when we start talking about quadratics. So what do? You factor any quadratic out that you see, and then look at the other denominators and determine if pieces of this denominator is in the other ones. So I can see right here that x minus 1 is in this, right? So I have this is in the denominator. X plus 1 is also in the denominator. So the least common denominator is x plus 1, x minus 1. Now that being said, what the common denominator is to then multiply the other denominators by what is missing. Meaning if this has x minus 1, it is missing the x plus 1. And again, the example I give is if you have a brother or sister and they get a certain toy when you're younger, you never want what they have. If they have something, you don't want it. Sorry, if they have something that you have, you don't ask your parents, why did I get one? You ask for what you don't have. So this has an x minus 1. It doesn't have the x plus 1. This one has an x plus 1. So what will it ask for? It's going to ask for the x minus 1. All right, so easy enough to figure out how to deal with the common denominators. But now the question is, what algebra do I have to do? Well, the numerator here, you have to multiply together using whatever multiplication technique you use. I have really started using the box method due to its ability to visually check itself very easily. So I'm going to use that. If you want to FOIL, that's okay too. Some students can even do this in their head, so that's acceptable as well if that's what you do. I'll show you how to do it in your head in just a second. So we end up getting 2x squared. That's a square right there, plus 5x plus 3. And the way you can do that in your head is you would do first and last, and then you would add the middle product. So 2x plus 3x is 5x. So it's not that hard if you are ready to do that in your mathematical ability. The denominator you're going to want to leave factored out for many reasons. Most importantly, it's going to cancel anyway with solving, so why spend the time foiling it? All right, so then I'm going to subtract this one's product. So again, I've got to use the box method or FOIL or whatever method you like to use. If I wanted to do this one in my head, it would be 2x squared, skip a space, plus 3, and then I would take -2 and -3 and add them together. If that scares you, then do it the longer way. Math is not about who wins, it's about who gets it right? So it's not about who gets it done first, it's about who has it correct. So if it takes you an extra 30 seconds and you're correct, please take that extra 30 seconds or a minute. All right, so there we go, and we have 2x squared minus 5x plus 3, and then my common denominator, I'm going to leave it unfoiled or boxed together. Now this side does not need to change because of the fact that it has the entire LCD, so I'm not going to change it at all. And what I do next is very important to understand what is happening algebraically. I do not just want to cross things out. You have to combine terms first, and this is a minus, so I actually have to distribute the negative sign to all of my terms. And as you remember in previous units, started from unit 1, I said to make sure that we put those together using the distribution, and then to come back and scratch this out so we don't accidentally get our wires crossed. So now when I combine it together, I'm going to have 2 minus 2, so that will cancel, right? 2x squared minus 2x squared. And then I'll have 5x plus 5x, which will be 10x. You can see how disastrous that would be if you didn't distribute that, because you would have thought the 5's canceled. So make sure you distribute carefully and scratch out. The 3's also cancel. My denominator is x plus 1, x minus 1, and that is now equal to 10 over x plus 1, x minus 1. Okay, so now, due to the multiplicative property of equality, meaning if I multiply both sides by this, it'll cancel, and same thing here, it'll cancel. You can just, if you know what you're doing, you can just cross these out as long as somebody asks you, what are you doing there? That's the multiplicative property of equality. So now I have 10x equals 10x, and, sorry, 10x equals 10, pardon me. So x will equal 1. Okay, and I did that, of course, by dividing by 10 on both sides. But now is where the domain restriction really is important. I want you to think about this just for a second, and this is why we leave these denominators factored out. My domain restriction on this problem is that x can never, x can never equal -1 or 1. Just to remind people where I'm getting that, if I set the LCD, that's one of the reasons we write it down. It's the least common denominator. So if you set that not equal to 0 and find what I like to call anti-solutions, meaning places where the graph is not allowed or the function is not allowed to exist, anti-solutions, you get the 2 domain restrictions. So this is saying that the answer can never be, I can never have -1 or 1. And when I take a look at this right here, I want you to just think about that. So look at that, look at that. I mean, that should make you just kind of go, what's going on there? If it can't equal 1 and my answer is 1, that means I have no solution, okay? To bring this out a little more broadly, if I take 1 and I plug it back in to right here, what would happen if I put a 1 right there? I would have 2x plus 3 over 0. That's undefined. It wouldn't matter here because I would have a 2, but if any part of it's undefined, the whole thing is undefined. Also, if I put a 1 here, 1 squared minus 1 would also be 10 over 0, which is undefined. And in fact, if I put this in the Desmos, okay, so if I put it in the Desmos, notice what I did. I said x equals 1, then I hit enter, and then I typed in the expression, as you can see here, using parentheses. You will have to use parentheses on everything you check in a calculator for this chapter. It says it's undefined. It also says it's undefined over here. So clearly, you didn't do any algebra wrong. You have created balance. The problem is that balance occurs at a restriction in the graph, and therefore it does not yield a solution. Okay, so the next example is very similar, but notice that in this one, there is nothing to factor. So this has what some people would call an LCD that is basically just a combination of all three things. Remember, if I need to find something that everything will divide into and nothing currently divides into anything else, the LCD would simply be everything you see, 2x times x minus 1. So then I come back into the problem and I say, okay, well, what's missing from the LCD? Looking at the LCD, what is missing over here? Well, I'm missing the 2x, right? So now that provides that particular portion of the problem with the whole LCD. So what is missing from here is it has the 2, but it's missing the x and the x minus 1. So what I like to tell students is leave that like that down there, but on the top, go ahead and distribute so that you're going to be already knowing what's going to be multiplied. Otherwise, you'll have two steps when you distribute whatever you have to do there. So what I did there is I did x squared minus x, and that is the same, but it'll be better for my algebra step, which comes up next. So here I have an x. I'm missing the 2 and the x minus 1, so I'll put that down here to kind of take note of what I need. But up here, I will say, well, I need to multiply by 2x minus 2, which is the same thing. Again, it's just going to make your algebra easier. So here, I just have to distribute, so you don't really have to do anything complicated other than distribute and make sure you keep your exponents accurate. Okay, so there we go. And then on the bottom, I'm just going to write the LCD out as I have it written over here on the right side. So no matter what it says here, I have this, so I'm just going to write it like that. The next portion is really easy as well. I just have 1 times those items. I mean, you can distribute 1 if you want, but it's kind of, it doesn't really do anything, so you can just write it down again. And then on the bottom, I have 2x times x minus x plus 1. It's x minus 1. I'm glad I saw that. Let me go back in, just update that. Okay. And then what we're going to do is we are going to have to box this one up. Because remember, this is really in a parentheses. You always have parentheses on numerators and denominators of rational expressions. It's an important thing to remember just in general about everything in this particular unit. So here we get 2x squared plus 4x minus 2x. And then minus 4, and that will be the numerator over here. So 2x squared plus 2x minus 4 divided by my common denominator of 2x times x minus 1. And, these problems, I should have mentioned it in the previous example, it is so important to just stop and make sure you didn't make a careless algebra error. Because one negative sign in this step means everything below it is going to be wrong, and then you won't be able to find your mistake. And again, I'm going to show you how to check it on Desmos to make sure that you do have it right. But you have to just go back. Okay, 2x squared plus 8x. Yep, right. You might even want to put a little check. Yep, I got that right. I got that right. So this one didn't change, but I'm making sure I didn't write it down wrong, right? So those are both right. And let's see here. Write it down correctly. X plus 2, x minus 2. So 2x squared, 4x minus 2x minus 4. These are my like terms. So, yep, looks good. Just make sure that you check your work because everything after the step relies on your complete accuracy of your old algebra skills. So here I'm going to combine my like terms. So 2x squared plus 1x squared would be 3x squared. And then 8x minus 1 would be 7x. Again, if you made that mistake and accidentally put a 9 there, all of a sudden it won't work. And I'll explain to you in a minute how you will sort of know if you made a mistake, and it's a critical thing to listen to in just a second. So over here we have this. Okay, and so we have 2x, x minus 1. And I do have the same denominator again, so it's like I'm multiplying both sides by this, and it crosses out, but the shorthand is to just say, hey, I'm using the multiplicative property of equality to cancel those. And then I end up with a problem from the quadratic unit. You know, that quadratic unit is so incredibly important. That's why I focused on the idea of making sure we know skills in that chapter, even when that chapter is over. Quadratics never go away. They're going to be in calculus with you. So how do we solve this quadratic? We set the side equal to 0 that will preserve the lead coefficient as a positive. And even though it's easier to move these two terms over here, I want to zero out this side. And the reason I want to zero this side out is so that I will maintain a positive lead coefficient. So 3 minus 2 is 1. If I did it the other way around, I would have had minus 1. And if I had minus 1, the problem would be much more difficult to factor and much more likely to produce an error. So I like to teach what I call defensive mathematics. Do math in a way that defends you from your own errors. Okay, so here we go. When we get a problem at the end that is clearly factorable, right? 4 plus 1 is 5. That's how you know if you made a mistake. For the most part, teachers aren't going to make you do all this work and then come down here and have to use a quadratic formula. I mean, it's possible, especially in an upper level math class. But if this expression right here does not easily solve, if it's not factorable, then you probably made a negative error somewhere. So just keep that in mind as you're solving. When you get to this step, if this thing is bananas, then the mistake is probably in the first step or a distributing error or something. Please heed that warning so you don't get yourself frustrated. Okay, so again, 4 is 1 times 4. If I go this way using addition, it would be 1 and 4. Then I use the zero product property to set these equal to 0. So x plus 1 is equal to 0. So x is negative 1. That is one of the solutions. And x plus 4 equals 0. So I would get x equals negative 4. That is one of the other solutions, potentially. Now, what do I mean by that? Well, our domain restriction at the very beginning here would be if I set 2x not equal to 0. Remember, my anti-solutions. So x is never allowed to equal 0. All right, so x can never equal 0. And x minus 1 can never equal 0. So x can never equal 1. So those are my answers that are not allowed. And when I go back and look down here, 0 and 1 are not my solutions. So they appear to work, right? So just to make sure that we don't frustrate ourselves, if I take a look at Desmos and I try negative 4, I did the smaller one first, I type in the original problem, x plus 4 using parentheses, x minus 1 using parentheses, plus 1/2, I get 0.5. You can toggle that to fraction mode. And if I put negative 4 into the original problem here, I would also get 1/2. And you could do this by hand. I mean, I just want you to think about this. If I put a 4 here in the x, right? I'm sorry, negative 4 here in the x, I would have negative 2 divided by negative 4, which is 1/2. So you can do that by hand as well, but if you want to use something like Desmos, you may. So you can clearly see that I've created balance. I have the left side of the equation equaling the right side. My other answer was negative 1, so I can just do that. It updates it immediately. I have balance there. So these are my two solutions, and I would want to write them in a bracket. Just like we've been doing since the very first unit. So the answer would be negative 4 and negative 1. Survived the domain restriction test, and they checked out. So those are definitely my solutions. So in these examples, we're going to be solving rational inequalities. We're still going to be finding an LCD, just like we did when we had an equal sign. So our LCD in this case would be x minus 2. And we're still going to be using domain restrictions as we are in every problem in this entire chapter. And that would be to set this not equal to 0. And so that would yield an anti-solution of x cannot equal 2 or a domain restriction. So to solve this, we're just going to do the same thing we had done. We're going to put a 1 on the bottom here. I don't need to multiply this by x minus 2 because it already has that. So I'm going to multiply by x minus 2 on the top and the bottom of only this one side. and then that will give me x plus 4 over x minus 2 is less than or equal to, distribute that, so you would get 4x minus 8 over x minus 2. And of course this will cancel, that's the theme here, right, because of the multiplicative property of equality, leaving me with this, x plus 4 is less than or equal to 4x minus 8. It's always important at this step to ask yourself, what kind of solving method is this? Since this only has an x, this is just a solving method from Algebra 1. All I have to do is get my letters on the left side and then get my numbers or my constants on the right side and solve this problem. So this would simply yield negative 3x is less than or equal to negative 12. And then I divide by negative 3, remembering my rules from Algebra 1, that when I divide by a negative, the inequality will reverse. All right, so my answer is x is greater than or equal to 4. The problem is this answer, right, is correct, but the problem is I have a domain restriction as well, and that domain restriction will interrupt this. What I mean by that is if I go here and I put 4 on, 1, 2, 3, 4, it appears that my answer will be, you know, a solid dot or a square bracket going this way, all right? But again, the inequality here is not the whole answer. I also have to analyze 2, and I have to determine what happens. And unlike in polynomial or quadratic chapters where you always have a check x check or x check x, this does not have that. This can be anything. This could be check check x, x check. So I have to go and analyze the number line using the same processes that we have used. Please keep in mind that if you have a domain restriction, this will always be an open circle. It can't include it. So what we're going to do is we're going to do that same analysis. We'll pick here, we'll just use x equals 0. And we're going to put x equals 0 into this inequality. It's pretty easy, right? You would have 0 plus 4 over 0 minus 2. And so that's going to yield 4 over negative 2 or negative 2. And the question is, does that meet the inequality that it has to be less than or equal to 4? And in fact, it does, right? So the answer is valid here. So this right here actually goes this entire direction with validity. I also need to check 3, right? So I need to check 3. So if I put 3 in there, I would have 3 plus 4 over 3 minus 2, which would be 7 over 1. So I have 7 over 1. And is that, in fact, less than or equal to 4? That would be a false. And for good measure, it's always a good idea to check something larger just to make sure you didn't make a mistake with the inequalities or make an error. It's always a good idea to check something. I'm going to use 10. You could use 5. It doesn't really matter. So here I would have 10 plus 4 divided by 10 minus 2. So that would be 14 over 8, right? 14 over 8. You can reduce that if you want, but remember the goal here is to determine if it's less than or equal to 4, and 14 over 8 is less than or equal to 4, so this is in fact valid. So now that I can see that, right, my answer is going to be negative infinity until 2 with the parentheses, and then 4 to infinity with a bracket. So negative infinity to 2, union with 4 to infinity. Okay, this will have parentheses because it's a domain restriction. It can never have an equal sign. However, this inequality, as you see here, will line up with the answer having a bracket on the 4, but only on the 4 because you can never include infinity anyway. So our next example is very similar. Notice what it has here is we have a 1, so of course there's a 1 on the bottom. And sometimes teachers will put additional things over here, but being that this is the first time you've ever seen it and we're only in an Algebra 2 class, I'm just going to try to make this an integer for the most part, just to make it so our understanding is clear about the number line analysis. So the LCD would just be x plus 2. If you had something over here, like you had like x plus 1, it would be x plus 1 and plus x plus 2. But for the time being, let's just worry about an integer. The domain restriction would be that x is not allowed to ever equal -2, because if I put -2 back into there, it would have a 0. And then we're going to solve it by multiplying this one by x plus 2 on both sides. Okay, and that will yield on this side x squared over x plus 2 is greater than x plus 2 divided by x plus 2. And just, again, common theme of solving. And this isn't the case for adding and subtracting, remember, only for solving. You can cross this out. And then I end up with x squared is greater than x plus 2. And I have a quadratic inequality like we saw a couple chapters ago. So we're going to move both of these over to the other side. Again, this next step, this last step, always involves some process you've already seen. And this goes into the whole math is the same thing, only different. It is literally the same thing here, but only different at the beginning. So this will be factorable. I mean, could it use the quadratic formula to complete on the square? Sure, but you should always think, if you get to this step and you're like, this doesn't factor, you should always think you maybe made a negative error or a mistake up here. So this problem is going to take 1 times 2 and move this way with subtraction. So I'm going to have my 1 and my 2 here. And then here I'm going to put a minus on the 2 and a plus on the 1 so that it'll come out to -1, right? 1 minus 2 is -1. So there are my factors. And what I'm going to do now is set them both equal to 0. So x plus 1 equals 0, and that'll give me x equals -1. And then also x equals 2, x minus 2 equals 0. So I get x equals 2. I jumped right to the answer there. Again, the problem with inequalities and with things that have an exponent higher than 1 is this inequality is lying, because it looks like it's saying this, right? It looks like it's saying go this way and then at 2 go this way. And remember, arrows going in the same direction in math indicates an error. So we're going to go up to our number line. We're going to put, I'll put 0 here. We have -1. We also have 2, so 1, 2. And these two items are going to have an open circle, and the reason they're going to have an open circle on them is because the inequality does not have an equal sign. But I also have to include this domain restriction that x cannot equal -2. Again, how did I get that? I set the LCD not equal to 0, and I solved. So I have to put both my solutions as well as my anti-solutions on here, and then check all of them as well. All right, so I have 4 things to check. Let's start easy and try 0. So if I put 0 into here, I get 0 over 2, right? 0 squared over 2. Is that greater than 1? The answer is no. Remember, 0 over 2 would be 0. It's not undefined, it's 0. So 0 is in fact not greater than 1, so that's out of the way. Why don't we check 10? Or you can check 3, it doesn't really matter. So if I put 10 in here, I would get 100 over 12, right? 100 over 12. Is that greater than 1? The answer is yes. Okay, so I figured out some of it. This would be going like that. Okay, so now I need to check something smaller than -2. So I'm going to use -10, and that would yield -10 squared. Remember, the negative is in the parentheses, so that'd be 100. And then divided by -8, right? -10 plus 2. Is that, in fact, greater than 1? And again, you don't really care about the answer. You care about the sign. This is negative. So it's a negative number going to be greater than 1. The answer is that part's false. So again, it could be false, false, false. We don't know. We have to pick something in here. So what in the world do we pick in there? Well, the only number that makes any sense would be negative maybe 1.5, which would be -3/2, and I picked this on purpose so that my students would learn it's not really about the complication here. It's really about is it positive or negative, because we're comparing this inequality to 1, which is a positive number. So the question is, if I put -3/2 into a square, right, it is going to become positive, right? So I have a positive numerator. This part's positive. And on the bottom, if I have -3/2 plus 2, right, is that also going to be positive? And it will. So sometimes you can eliminate your inequality right from that. And this one I have to do a little more work, and of course you can use a calculator if you would like. So the top would be 9 halves, and the bottom would be 1/2, and that would reciprocate and multiply and make 18 halves, or 9. So 9 is greater than 1. So this would in fact be valid. So there's my answer. You can see it right there. It would be -2 to -1, and then union with 1 to infinity, and everything would have parentheses because domain restrictions have parentheses, infinities have parentheses, and in this particular problem, this inequality doesn't have equals, and so that would yield parentheses. So in these examples, we're going to take a look at a solving technique that is really honestly very unique to rational equations. And its purpose is to actually determine what you added to get this numerator over here. What I'm referring to is, think of this as the answer to a question from a previous section where we added things. And our job is to determine, well, what are the numerators that we used to get this answer? Now, the purpose of this is actually for higher level math, but it's a very good thing to see now because it's going to show you a solving technique that otherwise you might not even be exposed to until much later. And the solving technique is quite interesting, and it's something you have never seen before. The problem starts, though, by just finding the LCD here, which would be x plus 5 and x plus 1, just like we would solve a normal problem, so nothing is changing. So over here, we multiply by what is missing. Same thing up here. Here we multiply by what is missing. Same thing up here. And then we end up with a very similar equation, but you do not want to distribute this a and this b. That will greatly overcomplicate the problem. So one underlying theme of all of rational problems, whether it be expressions or equations, is try not to simplify unless that simplification combines like terms or actually reduces the problem. If it doesn't cause reduction, it's not a good idea. So if I were to distribute this a and this b, that will cause complication, right? So we want to avoid complication when we do problems. Okay, so here what we're going to do is we are now going to combine our like terms over here. So we don't have any, so we just have a numerator, right? That's just going to be a x plus 1 and b x plus 5. And since we've been solving for a while, it might be, you can kind of skip the next, there is a step where we put this here and then we cancel it out. This step, if you know it's going to happen, why not at this point say, okay, I've learned that enough. I'm sort of good with just knowing that it's going to be gone in the next step. Okay, so we're left with this. So what do we do to solve this? Because we're trying to solve for a and b. So what we do is we use a solving technique called zeroing out. Now, what does that mean? If I were to let x equal -1, it is going to cause this term to go to 0, right? -1 plus 1 is 0. Now, why is that helpful? Well, over here, it will not zero out. It'll give me -1 plus 5. And over here, it'll give me -1 minus 3. So while this is canceling out, students always ask, why did you pick -1? So I could get rid of a, right? I wouldn't pick 7 to get rid of a. Why did I use a first? Because it's alphabetically first. So it eliminates it, giving me -4 here. This is gone, and then I have b times 4, and now I can very easily solve for what b is. B is -1. And I'll go back and explain what that means once we find what a is. So that's b. And so now, if I get rid of b, it will give me a. So I'll do the exact same problem, but now I'm going to let x equal something that will cancel b, which would be -5. So if I let x equals -5, then I would have b times -5 plus 5. Where did I get the number from? Again, I picked the 0 of this. I set this equal to 0 and solved it. All right, so then the a would be a times -5 plus 1. all right, and that would equal negative 5 minus 3. So this zeroes out, right? This becomes b times 0, so it zeroes out. This becomes a times negative 4, and this becomes negative 8, so I can very easily solve for a. A is 2. So what in the world does this do for me? If I come back up and plug them into the numerator, so if I come back up here and I say, hey, b is negative 1, right? So b is negative 1, and a is 2. If I were then to distribute this and distribute this and combine like terms, I would yield this answer. So you may say, like, well, what is the point of that? That is an incredibly powerful thing later in math, specifically in calculus. But the technique is something you haven't seen, the zeroing out technique. So I'm going to look at one more example. And this example has like an extra x in it. Okay, so no change, right? What we would do is we would factor x plus 5, x minus 5 to find the LCD. Right, so you have your LCD here. You're going to multiply this by x minus 5. You are not going to distribute because that causes complication, not simplification. Anything you do in math that makes the problem worse, back up that bus, right? That's not a good idea. So here we would have x plus 1 over our common denominator is equal to ax x minus 5 times, plus b times x plus 5. And these have a common denominator, right? But we know it's going to cancel. So at this point in the game, we'll just call that part good. So how do I zero out a? What I'm going to do, and this is very powerful, even though there's an x here, if I let, right, x equal 5, if I do that, that's going to go into here and create 5 minus 5. And yes, I will have a 5 out here because it also has to go into here. But a times 5 times 0, right? 0 product property, this is 0, right? Because if this goes to 0, then it doesn't matter what that is. That's what's so incredibly wonderful about this technique. So I'm going to put the 5 over here as well. Now notice the b doesn't have an x, but we'll deal with that when we solve for the next one. So b would be 5 plus 5, so that would be 10b. And then over here we have 5 plus 1, so that would be 6. And so we have the equation 6 is equal to 10b. So if I divide by 10, okay, and again, just to remember how to reduce things the way I've explained it in this chapter, find the common multiplication fact, 2 times 3 and 2 times 5, and that will give you the reduced answer for b, right? So b would equal 3/5. All right, so there's our b value, and if I cancel out b by letting x equal negative 5, that will cancel out the b term, right? Because b will now be b times negative 5 plus 5. So that is now zeroed out, right? B times 0, gone. But if I put negative 5 into here, I would have a times negative 5 times negative 5 minus 5. So I'm going to have to do a little algebra there, but it's just combining like terms. And then over here, I would have negative 5 plus 1. So negative 5 plus 1 is negative 4. So I'm going to end up getting a times, and just go in the order of operation. So this would be negative 10, and then times negative 5. So this comes out to 50. So then I divide by 50 on both sides, and I get this for a, which would be, if I reduce that again, best way to reduce is to take negative 2 times 2, and then 2 times 25 is 50, and then cancel out the common term, just like I did over here. And so a is going to come out to negative 2/25. Now you may say, wow, those are some crazy fractions for a and b to b. Meaning, again, what that means is if I come up here and put negative 2/25, right? And this would be 3/5. And you're probably like, wow, that is a mess. You're telling me you want me to distribute that here and combine like terms? Yes, you will in fact get x plus 1. That is what this is saying. Now, that being said, when you do this eventually in calculus, the beauty is these two crazy fractions can actually be pulled out of the formula, making your life incredibly easy. So this is a technique you're learning so that hopefully it will kind of be there for you later. And if you're watching this video as a way to learn how to do partial fraction decomposition in calculus, you know that those things just get pulled out. So that sure does make your life easier. So again, partial fraction decomposition sounds complicated, but it actually teaches a technique of solving by zeroing out that you wouldn't learn otherwise.